In previous video, we talked about representing numbers in different number base and converting them from one base to another, which you can watch here. In this video, however, we want to talk about performing operations on binary numbers. To get us started, we will first look at adding two numbers in base 10, and then in base 16, and finally in base 2. Let us start with base 10. We want to add two numbers, 27 and 18. As you know, to add two numbers, we first add 7 and 8. The result is 15. And since we cannot place two digits in a single position, we write 5 in the 1 columns and carry 1 to the tens columns. Then we add tens columns, which equals 4. So final result is 45. Now let's take the same numbers and convert them to base 16. In that case, the representation of 27 in base 16 is 1b, because we have 1 16 and 11 ones. The number 18, since it has 1 16 and 2 ones, is represented as 12. Now we add b and 2, which gives us 13, and symbol for 13 in base 16 is D. We also add 1 and 1, which gives 2. So the final result is 2D. If we now convert this 2D back to base 10, it should give us 45, because 2 times 16 plus 13 equals 45. Now we set the base 2 too. Here we convert numbers from base 16 to base 2. To do this, for each digit in base 16, we consider 4 bits in base 2. Since we have 2 digits, this gives us a total of 8 bits. The number of 1b in base 16 is equal to 0001, 1011 in base 2, and add the number 12 in base 16 is equal to 0001, 0010 in base 2. Now we add these two binary numbers together. 1 plus 0 equals 1, 1 plus 1 equals 2, and the representation of 2 in base 2 is 10. Since we cannot place two digits in one position, we write 0 and carry 1 to the next column. Now the result of 1 plus 0 plus 0 equals 1, and 1 plus 0 equals 1. Similarly, 1 plus 1 becomes 2, so we write 0 and carry 1 to the next column. 1 plus 0 becomes 1, 0 plus 0 equals 0, and finally 0 plus 0 equals 0. In this way, the result of the addition in base 2 is obtained. Now, we convert this number from base 2 to base 10, we expect to get 45, because 32 plus 8 plus 4 plus 1 equals 45. Now, we need to point out a very important point. Suppose we have two nibble numbers such as 1101 and 1001. If we add these numbers together, 1 plus 1 equals 2. We write 0 and carry is transferred to the next column. 1 plus 0 equals 1. 1 plus 0 equals 1. 1 plus 1 equals 2, so we write 0 and transfer 1 to the next column. However, because the result of addition does not fit into 4 bits, in this case we say that an overflow has occurred. Now that we have learned how to add numbers in base 2, it is a good idea to talk about subtraction. To perform subtraction, we need to know how to represent a negative number in base 2. Then, by adding the first number to the negative representation of the second number, we can compute the result of the subtraction. To represent the negative of a number in the same base, we use a specific method. Suppose we have a 4-digit number in base R. For example, A0, A1, A2, A3 as a digits of a number. The first step is to compute the r minus 1 complement of that number. and then add 1 to it to obtain the representation of the negative number. To compute the r-1 complement, we subtract each digit from r-1 and replace it with the result. r-1 minus a0, r-1 minus a1, r-1 minus a2, r-1 minus a3. Then we add 1 to the resulting number to obtain the r complement. Finally, to perform subtraction, we add the first number to the r complement of second number, and the result of subtraction is obtained. Okay, let's first give an example in base 10. Suppose we want to subtract 18 from 27. As we know, the result is 9. However, a computer does not understand subtraction in the way we do. A computer can only perform addition. Therefore, to do this, we have to add 27 and the tens complement of 18 in order to obtain the result of subtraction. To find the tens complements of 18, we first calculate its r-1 complement as follows. 10 minus 1 minus 8 equals 1. 10 minus 1 minus 1 equals 8. As a result, the number 81 is obtained. Now we add 1 to 81 to get the r complement, which gives 82. Next, we add 27 and 82, which result in 109. Since the result of our subtraction should not have more than 2 digits, we ignore the leading one in 109. And as a result, we obtain 09, or simply 9. Now, let's give an example of subtraction in base 2. Suppose we want to subtract 5 from 12. As we know, the result of this subtraction is 7. First, we convert 12 to base 2, which becomes 1100. We also convert 5 to base 2, which becomes 0101. Now, we need to calculate the r-1 complement, or 1's complement for the number 5. The good news is that calculating the 1's complements for binary number is very simple. You just need to flip the bits. So, for the number 0101, the 1's complement is 1010. Next, we add 1, which is 0001, to add 1010 to obtain the r complement. Now, we add this r complement to 12, which is 1100 in binary. 0 plus 1 equals 1, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 2. We write 0 and a carry is generated, which is discarded as an overflow. As a result, we get 0111, which represents the number 7 in base 10.